Today we'll be talking about concurrency on global scale. We all know, probably from university or from your own work projects, about the concurrency on like host level. So you have a server, you have multiple processes, multiple services running on the same server. You share the same resources, and you need to like balance them between all the processes. And this is easy. Like we have methods to do that. We have logs. We have semaphores. We have different approaches. And the idea here is to stick to the patterns, do what you are told, and follow the practices. And you probably won't face a lot of issues with this. The problem on global scale is that it's quite the opposite. So you actually have to break things to make it work. You have to not follow the practices, the best practices, to be able to scale your application globally. And today I'll try to tell you how to do that. So on global scale, it's more about trade-offs, about choosing what we want, what we need to do, than it's about actual practices. So there's a thing called CAP theorem. It was created in 1998, so it's quite old, but it's still valid. And it's actually mathematically proven that out of 3 things, so consistency, availability, and partition tolerance, you can have at most 2 of them. You cannot have all 3 of them. But what those words mean, so consistency means that all the clients, so all nodes in your network, can see the same data at the same time, regardless of updates, deletes, and other operations that you can do with the data. Partition tolerance means that if your system gets partitioned, either intentionally or by some network failure or any other event, it still has to continue to run to deliver value. The third thing is availability. Here the definition is slightly different than it's in, for example, ACE. So availability is that the system continues to operate and to provide feedback on status. So even if the system returns error, it is still considered available. So to go on why only 2 things out of 3 are possible, we have to go through the fallacies of distributed computing. Those 8 fallacies were created also in 1990s by guys called Peter Deutsch and James Gosling. And they summarize 8 things that programmers usually forget about or they assume it to be true. Those assumptions are false, and if we assume them true, it will cause either some problems or lack of value, or it will cost a lot of money to actually redesign our system. So the first fallacy is that the network is reliable. We all use networks. We probably assume that like enterprise type of networks are reliable because we have a lot of redundant networks, redundant links. We have multiple topologies that can handle our load. But this only decreases the probability of failure. And probability is not really something that we can trust 100%. The second fallacy is that latency is 0. So it's not. Actually, a guy called Albert told us that the light does have some speed, and we cannot actually cross this boundary of speed. So our information cannot travel faster than some boundary, and we have to take it into account in our systems. The third fallacy is that bandwidth is infinite. So you can set any amount of data and over the network. But again, it's not true. With bandwidth, it's slightly easier because you can just add additional bandwidth, but it's still limited. So if your link gets saturated, your cable is full, your like optic wire is full, you cannot go over it. You will just lose data. The fourth fallacy is that the network is secure. It's almost secure, like we have protocols to make it more secure. But we all heard of, for example, Heartbleed problem that's pretty much made the whole network insecure. And also, I don't know if you know how much it costs to actually forge a certificate, SAH1 certificate. So it's about $70,000 to forge a certificate. So it's not like huge amount of money, it's doable. The fifth fallacy is that topology doesn't change. It might be true in Poland. We have Marriott 13th floor, but it's not in the global scale. So topology does change, and it does change frequently. And it also happens inside your data center. If one link fails, the topology can change, and your network, your data can go through some different routes. The sixth is that there is one administrator. And of course, he works 24/7, he doesn't party, and he's always available. Yeah, not really. So there are multiple administrators, multiple participants in all the systems, and they all have different goals. One example is Edward Snowden, that you probably know. So he was one of the administrators, but his goals were quite different than his manager's goals. The seventh fallacy is that transport cost is 0. But it actually does cost to send the data over the network. And the cost is either direct, so you have to use some energy to actually push data into the network, but it can be direct as well. So there are infrastructure costs, like the recent network, like wireless bandwidth, that's costed several billions in Poland. And also the maintenance of the network and the engineers that keep it running, they all cost money, so transport is not free. The eighth fallacy is that the network is homogeneous. You might think so if you put all the same type of hardware, all the same type of links, but it's not really. Like, every server does some background processing, and it can do it in different times, depending on different factors. So your network is not really homogeneous. All the links behave differently. All the switches or network infrastructure can have different characteristics. So those were the 8 original fallacies, but there's the 9th fallacy that was created in 2009, so it's more recent. And it's about location. Location is irrelevant. We tend to assume that we can just put server anywhere and it will just work, but they won't. There are politics in play. There is just a geographical distance in play. For example, if you put your server in United States, you will never get latency lower than 150 milliseconds. It's just the amount of time that it takes information to travel there and back, and you just can't go over it. If you put your server in China, then you probably don't get any traffic because you just can't get there. So location is actually relevant. So we'll divide these problems into 3 categories according to the CAP theorem. And first, we'll talk about data consistency. So according to CAP theorem, data consistency is about all the participants of the system seeing the same data at the same time, regardless of updates, deletes, or changes to the data. We can make this definition slightly less constraining, and we can make it so that all the nodes have enough information to proceed, and they do not collide with each other. That gives us a lot of breathing space, which we'll see in a moment. So what are the problems with data consistency? The problems can vary significantly, but one of the most common examples that probably all of you use is credit card processing. So your bank knows how much money do you have on your account, and it actually wants to keep you not spending money that you don't have. So it has to keep consistent information about the balance of your account across pretty much the whole world where you can pay with your card. This is one of the problems. The same thing goes with electronic transactions like PayPal or similar, where they actually need to know how much money do you have at a given time. But the problem is widespread. So if you use relational database, it is also there. You have transactions that kind of separates you from the problem, but it was just resolved for you. So what are the solutions? There are several different approaches that you can take to actually solve the data consistency issues. And the first, and probably the easiest one, is optimistic locking. It's called optimistic because the assumptions are very optimistic, and it will actually work only if you can handle long timeouts and if the data that you are processing is not time critical. So optimistic locking works in a way that it stores some validation information that you can use when you are updating data. So instead of overwriting the data that somebody previously modified, you just check if the condition still holds true, and then and only then you can execute the update. So in standard model, first you read some data, then you update it, process it, or whatever, and then you persist the result. With optimistic locking, you first read the data, you process them, update it, or whatever, and then persist only if the data was not changed before. There are a number of ways to do that. Actually, some of the systems that you probably use also use optimistic locking. One of the examples is SVN or Git. So in SVN, the log part was the revision number that's actually changed with its revision, and you cannot commit if your latest revision is before the central is stored. The same goes with Git. In this case, the log part is actually your parent commit on given repository. So you cannot commit if there is some, like you cannot push the other repository if there is some later changes. Optimistic locking can be very easily implemented in pretty much any data store. You just need one additional field where you can store, I don't know, timestamp or just some random number, and use this as a condition when you are persisting your updated information. So the second approach to data consistency is eventual consistency. So sometimes you just don't care when the data will be updated. You just care that it will eventually get there, like this guy sleeping there. And this is useful if, again, your data is not time critical, and you actually can allow a long time to persist this data. The example from real life can be, for example, the replicas of database, read-only replicas, because the way they are maintained in the same state as the master is basically some updates are sent and are eventually applied to the read replica, but it doesn't happen in the same time. So eventual consistency is even easier to implement because you just need some message paths where you can send information about updates, and then each of the clients can consume them at any given time that they actually need those data. The third class of solutions to data consistency is actually redefining the problem. So sometimes it's not really worth spending all the effort to solve the problem. It's better to make it into some other problem. And it happens a lot with big systems. Like the example that you might be familiar with is the NoSQL data stores. So the goal of this class of systems was to actually store data on a massive scale, to be able to distribute it around the globe. But they had to do some trade-offs. So instead of thinking, how can we do that with providing data consistency, they redefined the problem. They said that we just want to store this data and we will not be consistent, so it's your problem. So they redefined the requirements and how they approach the problem. And it actually might work in your systems as well. So it's not always necessary to solve the problem. If you talk with your customer or manager or just project owner, it might happen that some of the features are less important than the others, and redefining the problem can help you a lot and save you a lot of money. The fourth case here is the leader election. We'll talk in more details about leader election in the future, in the next slides, but the general idea is that we elect a leader among our fleet who will know and who will be a central point of synchronization in our system. The downsides of this is obvious, so we have a central point of failure, and if we by some chance have two leaders, then we can have much worse inconsistencies than without a leader. But we'll get to that later. And the fifth solution here is idempotent requests. This actually solves only part of the problem, because this is about two systems updating the same data at the same time. So let's say you have some data about your customer, and you have the accounting system and orders system. And both can change the actual customer entity. So what will happen in like standard way if we have two systems that at the same time start the processing? They read the same data. The first system processes the data and stores the updated version. So the Q1 is new and Q2 is old. But at the same time, the similar processing happened on system 2. But the results are different. So system 2 stores doesn't change Q1, but does change Q2. When this happens, and we don't have any other like safety measures in place, the later result will just override the error. And this is like not desired situation. So idempotent request is all about making your changes not intrusive to others. So the idea is that you can repeat your request as many times as you want, and the end state of the system won't change. So in this case, instead of just updating the whole record, the first system will just send information, okay, I want to update the Q1 to the new value, and the second system will send the same information about the Q2. In this way, those two systems do not collide, and we can actually keep our data synchronized across multiple systems. And it's actually one of the most common approaches to resolving such data clashes. So another solution is two-phase commits. We probably all heard about it because, again, it's used in tools like SVN or probably another libraries for distributed synchronizing. The idea here is that, again, we elect a leader, but it is slightly easier because a leader can be different for each transaction. So we don't need one host that will serve as a leader for everybody. We just need a leader for transaction. It can be the host that is initiating the transaction or that is handling the customer request. And this host asks everyone to do some change, do some processing. Then the second stage of this this process is for all the hosts that are participating in the transaction to actually send the information back to the leader whether the transaction was successful. So they send either, yes, I did the transaction and the change, or no, I couldn't do that. The thing is that those, let's call them clients, are not allowed to actually commit the changes. So they should keep them in some non-persistent state for a while. And based on the replies from all the other clients, the leader decides what to do. So either to commit the transaction or to just abort it. And it sends the message to all the clients as well to follow suit. This provides some measure of safety. It is problematic if there is a problem with connectivity between hosts. So you would need actually additional measures of safety like timeouts or default behaviors or anything like that. But it can be done. Again, such example of such approach can be found in SVN or CVS that was predecessor, but also some distributed transaction management systems use this protocol, let's call it, to synchronize states of different nodes. So the second part of CAP theorem was partition tolerance. And by partition tolerance here, initially the theorem says that it's about partitioning the system in an unexpected way. But we can slightly extend this definition. And we can also consider partitioning the data. So this chapter will be about preparing your system to be able to handle both partitions in a physical sense. So two parts of the system get separated and lose connectivity to each other, but also in the data part. So like we have a set of data, and we just partition it in some way that allows parallel processing in different areas at the same time. So the first solution here is actually cache, and it is widespread. It's the simplest solution to implement, and it is actually implemented in pretty much any solution that you are using. There are also solutions like out-of-the-box libraries that you can just attach to your system, and they should work. So cache works starting from operating system and TCP/IP stack through your database, memory paging, and pretty much all the other resources that we have. A cache is, as I said, the easiest to implement, but it also has some drawbacks. So cache can get stale. Like the data in the cache can be updated in the central repository or like in the general system. But if your cache is not updated, then you're probably processing the wrong data to start with. Kind of like part of the cache approach is also the queuing systems. So in Java, it would be JMS type of systems. There are like solutions like AWS, SQS, and stuff, which can work as kind of a cache. So they are caching the requests. They are just a queue for the requests arriving at your system. And this approach can help you handle the problem of your system being partitioned physically. So if the network link is broken, and we assume that it will be restored in some future, you can use cache to actually store some actions to do some processing to perform, and continue working until the connectivity is restored. You can also cache some other things, not really requests. You can cache parameters. You can cache state of other components of your system. And also you can cache the responses if they are deterministic for a given set of parameters. This way you can handle like lack of connectivity between multiple parts of your system. The second class of solutions is self-organizing fleet. So the idea here is to have a predefined way of dividing work into the fleet of hosts, so that everybody knows where one particular work should go, and only this part of your system picks it up. This works especially well in like request response system, where you can store some, like process in parallel multiple requests, and they are not dependent on each other. So in case of self-organizing fleets, the knowledge about how to actually partition the work and how to load it through your entire fleet should be stored inside the algorithm. So there are two ways to do that. The first one is consistent hashing. So consistent hashing means that you assign a hash value for each of your requests or each unit of work that you need to do. And based on this value, you assign it to a part of your fleet. In terms of consistent hashing, the difference between like standard mapping between some hash and some part of the fleet is that the part of the hash domain that's given host or server or part of your fleet is doing can change. So this works in a dynamic environment where you have like 10,000 of hosts and they are added and deleted from the fleet as required. And the way it works is that any server that joins the fleet that is doing the processing creates multiple like parts, multiple points in the hash domain that it will process. Those points you can see as different colors here. And when the request comes, it checks all the hosts that are part of this domain and assigns the work to a host that covers this particular piece of the circle. Yeah, there are two two important factors here that we have to be aware of. The first one is the hashing mechanism that we are using. So a hash by definition is just some identifier of a request that is shorter than the request itself. We have a lot of hashing algorithms like MD5, SHA1, but we can use pretty much anything. We can use the ID of the customer or the initials of the customer or the first name. The problem here is that this hashing function for consistent hashing to work efficiently has to be uniformly distributed. So SAH1 algorithms are pretty good for that because they give pretty much random string for any kind of data that you provide. But things like initials of the customer or ID of particular request are not very good because they will create hotspots on your system and will probably overload just this one partition. The other thing here is why consistent hashing is better than actual mapping between hash and some partition is that when part of the fleet is disabled or just goes offline or something else happens, consistent hashing provides the most optimal values in terms of how many requests has to be redistributed to another partition. So in terms of consistent hashing, like ideal consistent hashing, the number of redistributions is the number of keys divided by the number of partitions. So the smaller you have the partitions, the less changes you have to make to the actual data. The second type of self-organizing fleets is actually sharding. And sharding is probably a term that you know from relational databases. So sharding means that you define a cut point where you separate the data. And this cut point can be pretty much anything. Like the most common ones are timestamps. So for each day, or for each month, or for each period of time, you create a new partition of data and you assign it to a new place to storage or new part of your fleet to actually process. This sharding is also used in NoSQL systems. For example, Google's Big Table uses sharding for that. And the way it works is that initially we have one, what they call tablet. And this tablet has a size limit. So if the size limit is breached, it is divided in half into two separate tablets, each of them containing just like half of the keys. And it just continues to do so when the data is attached. They also have some mechanism to merge back very small partitions. But that's basically sharding. So sharding means dividing data by some given conditions, while consistent hashing is just algorithm of assigning data based on the actual content. The third class of solutions here is the circuit breakers for partitioning. And the way it works is that if certain condition happens, so if there is a problem or if we encounter an error or if there is a broken network link, we just change the way we operate. It can be implemented in multiple levels. So, for example, the network routing protocols also implement this mechanism to route the traffic. So if one of the network links is broken, then all the data is routed through some alternative backup link, of course, if it's possible. But it is also possible in the software. So we can create actually logic that does approximately the same thing or uses some other subsystems or uses some other algorithm that it can perform locally or route the same data to some other partition of the system or just ignore the data and schedule reprocessing later. And there are some libraries to do that. For example, there's a Hystrix library from Netflix that works with Java and allows you to do the same thing. The idea is to not like throw errors, not to go into error condition, just to process maybe slightly longer with slightly higher risk, but just do the processing anyway. The example from real life can be met, for example, in the United States. If you pay with a card in the United States, and the connectivity of the terminal with the bank servers is not really working, the guy will just copy the number of your card and it will be considered paid. And this is the example of actually circuit breakers. So the strategy changed when some problematic conditions happened. But the value is provided, so you can't pay without using direct cash. And the fourth class of solution is leader-based. And in this case, we have to elect a leader who will tell everybody else how to do the partitioning. The leader election can be done in multiple ways. There are actually frameworks and whole systems dedicated just exactly for that reason. But the simplest solution requires you only to have some local, like distributed log mechanism. So we can use relational database with like logs on tables or rows. You can use Apache Zookeeper if you want, or you can use some NoSQL stores, which is also possible to do that, even with eventual consistency. So a leader-based approach, most commonly used for now is, for example, load balancers in web traffic. So we basically have a leader, which is a load balancer, who decides where the request should go. It can decide on different conditions like the actual load on the host or just do the round robin. But the idea is the same. There's one central point which distributes all the requests to proper places. The problem with this approach is, of course, that we have a central point of failure. So if the leader fails, then again, we don't know how to proceed. So we have to either elect a new leader or just wait until the leader gets back to life and is able to process the request further. And there's another problem when there are two leaders. So if we elect a new leader and the old one gets back to life, then we can have two leaders with two different sets of information which can be colliding with each other. So this has to be also solved by other means. There is no golden standard here. And this is actually the most risky approach to partitioning, because it introduces the biggest number of problems by itself. The fifth approach to partitioning is something that's called Paxos protocols. So Paxos protocols is a set of algorithms and protocols that allow you to partition your requests based on some kind of conditions. It is slightly similar to two-phase commit, but the difference is that it actually is distributed. So two-phase commit requires one central leader. Paxos protocols does not require a leader per se, but one of the hosts is elected a leader in the process of voting. But it has some methods to actually compensate for multiple leaders election and to like regain the stable state in such situation. The Paxos protocols are quite hard to implement, but thankfully they are available in a lot of libraries. And for example, the Chubby, so that's Google's distributed transaction manager, uses those kind of protocols to work. Same for Neo4j, it's like a graph database. And also Apache Mesos, which is a framework used, for example, by eBay, Airbnb, and a lot of bigger IT companies. The problems here with the Paxos protocols are first, implementation, so it's not easy to implement them into your systems. And the second problem is, the main problem is about implementation. And the way Paxos protocols works is that you have to actually choose the criteria that you are interested in. So it can be more resilient, it can decide faster, but there's no like one set of rules that will follow, that will fit everyone, and you have to make this decision yourself. The third part of CAP theorem is the availability. So availability is about your system giving a response. So it's not about strictly working and providing all the value it should. It is about being able to tell your client that it has some problem. So if it cannot continue the work, it should just return the error response code or display some message or static value or whatever we define. So the first approach to actually how to handle this is client-side processing. It is more common nowadays with the advent of frameworks like, I don't know, something for JavaScript like Angular or anything like that. But it's not really limited to web processing. So any kind of client-server interaction can have client-side processing. And it's also an example of like caching values on the client side. So client-side processing can work in basically multiple different modes. So first, it can be completely client-side. So if your service is providing some computation, I don't know, it's calculating the P number up to billionth point of precision, you can actually do the same on the client side, but the idea of having a service for that is to do it faster and probably better. But if your service is not available, then the client can do exactly the same, but it will just take more time or be more risky to actually perform this. The second possible mode of work here is a service degradation. So your client can be able to do part of the processing, but if it loses connectivity with the server or the rest of the infrastructure, it might actually lose some updates, or it might not be up to date with the current state of the system. And that might yield the results inaccurate. So the example is some accounting system. It has some state about, I don't know, the orders that are placed in the with your company. And some manager just requests a summary of all the orders or the total value of the orders. So this accounting system is able to do it without the most recent data. But if it doesn't have those most recent data, then the value it provides will be slightly inaccurate. Sometimes it's acceptable, sometimes not really. But that depends on the actual business case. The first option is to just throw an error. So the client-side processing can also be used to just return some default value, some static value, display a page like, hey, I can do that. That's also fine, at least in certain conditions. So the second thing is service degradation. It can actually be used to provide similar value within your service. And you can imagine that a lot of services are just a newer version of some other older services. They are faster, they provide more capabilities, they can scale better, they are cheaper to operate, but they basically do the same thing, just in a different way. So sometimes it's worth to keep those old systems running, just in case your new system fails, and you can redirect all the processing to the old system. Yes, it will take more time, it will cost more, but still you will be able to provide the value to your customers. It will be degraded value because you can have some SLA like the latency, maximal latency for your request, and you might not meet those SLAs, but still your service will be working and delivering some values and returning some data. The third class of solutions is availability zones, and this is actually quite common in systems that operate on a global scale. So to mitigate the risks of, I don't know, network failure or some natural disasters or anything like that, you can deploy your system into multiple locations. How you do that actually depends on the system itself. The disadvantages are, of course, the cost. So you have to keep infrastructure in pretty much every place that you deploy your system to. So you need as well engineers, you need somebody to maintenance, you need to buy hardware, and you have to probably rent a data center or build one. But the benefits are sometimes more important than the cost. So, for example, if you are operating a site like eBay, you don't want all your requests from around the world to go to the United States and then back through the links, because it will just take more time and it will be less reliable because there are more pieces in between. And also, it will probably cost you more in terms of transfer and like customers being not very satisfied with the value that you provide. So what you do is you deploy to multiple zones. Those can be geographic, those can be logical, so we can have actually one data center with just 3 racks or 3 servers that have the copy of your systems. And the idea is to like route part of the customers to particular zones. Those zones can be completely replicated, so we can have the same state in all of them. This can happen, for example, with PayPal or any other similar like systems related to money. But you can also have completely different data sets in each of the zones. And this is actually the case for example, eBay, which basically have separate data stores and data sets in each of the zone. So some of the auctions are not available in ebay.co.uk, but they are available on ebay.com. If you create an account in one place, you have to wait some time until it becomes available on the other place. You can actually break eBay by creating an account with the same names on 2 different websites. I think they managed to fix that, but once they had quite a large problem with that. So the problem here is to actually synchronize the data. So we go back to the first chapter of our presentation about data consistency and how can you keep those in sync. It really depends on the type of the system you are building, but availability zones can help you, but they are like one of the most costly solutions to the problems that you can implement here. And the 4th type of solution here is actual redundancy. So we often think of redundancy in terms of hardware. So we have redundant memory, network links, disk arrays, servers, racks, or whatever. But actually, redundancy should be also possible in terms of software. So, as I mentioned before, we can just keep the old system running as well, just in case the newer one fails and we have to switch over. We can also deploy 2 completely separate instances of your system and keep one as warm replica of the other, just to have this redundant state. So redundancy solves the most common issues, and it's probably one of the most widespread solutions to the problems with distributed systems. But again, it's very costly because, well, you have to keep part of the system and keep it running, pay for the electricity, but it is not actually doing work. It is problematic to keep in sync both the copy and the original system, and it is not really optimal in terms of resource utilization. But sometimes it's necessary, like with hardware and power sources and other things like that. So this was mostly it. So basically we've talked about the CAP theorem, which proves that there are 3 features of your system that you cannot have at the same time. And this is consistency, availability, and partition tolerance. You can choose at most 2 of them. Usually it will be only one of them. So this is trade-off, like building distributed systems that scale massively, that work globally, is all about trade-off. There's no one golden standard that you can implement and it will just work. It all depends on what are your requirements, what do you need, what do you want, and what your customers want, and also how much money you have to build and maintain. We also went through the fallacies, which are the reason why you can't have all of them, and through several of the solutions to particular class of problems. Thank you.